So in the previous page, we have mentioned how to define dynamic programming-based algorithm for optimizing the queries. And in this step, one important part actually is to compute the cost, right, for this Q. We mentioned we enumerate all the potential combinations of Q prime and Q prime for computing the cost of this Q, right? The one introducer knows the cost will be defined cost for the Q here actually. In the question here we have, it will be how to define cost on the plane Q prime joins plane Q prime. How to define this term? So we can define this term according to the following pages, and to illustrate this term, we can use a simplification actually. When we're computing the cost for the join of two planes, we can define the cost to be equals to what? If we have two planes P1 and P2, this P1 and P2 they are actually the subqueries we can get. Which cover a subset of the relation we mentioned before. And we want to calculate the cost for P1 joins P2. P1 and P2 they are the subplanes. And we define cost to be equals to the cost of P1 plus the cost of P2 plus the cost for the intermediate results. It equals to the size of the intermediate results. What is the intermediate result? It really depends. If P1 is a join, in other words, P1 is a combination of some other relations or some other planes. If P1 is a join, then the size of the intermediate result will be equal to the size of P1, because we have to store this intermediate result into the disk or into the memory, right? If P1 is a join, then the cost will be equal to the size of P1, otherwise the size will be 0. It will be similar for P2 as well. Here, if both P1 and P2 they are just relations, they are not planes or subqueries, if so, then the cost for the intermediate result will be equal to 0 actually. Because if we're just doing the scanning, the cost will be equal to 0. You can follow me, right? So if either P1 or P2 they are the joins, then the cost for storing the intermediate result will be equal to the size of this kinds of P1 or P2. Otherwise, the cost will be 0. We have some concrete examples. If P1 and P2 they are both relations, they are just individual relations. If so, then the cost of R1 joins R2 equals to the cost of R1 plus the cost of R2 plus the cost of intermediate results, right? However, here we mentioned that cost for scanning equals to 0. In other words, the cost for the R1 joins R2 will be equals to 0. You can follow me, right? However, here if we are computing the cost for the R1 joins R2, this is the P1 we define here. This is one of the subplane, right? It will further joins R3. This one will be equals to what? It will be equals to the cost of R1 joins R2, right? Plus the cost of R3 plus the size of R1 joins R2. Because we define the cost for R1 joins R2 to be equals to 0, this one will be 0, right? Similar for this one, this will also be 0, right? Because it just covers scanning of the cost, right? The cost is 0. Therefore, the cost for this term will be equal to the size of R1 joins R2. You can follow me, right? So this is the way we define the cost for simplicity for the dynamic programming-based optimization algorithm. Okay, so this is the algorithm we have covered already. So in the next class, we will show you how to use this algorithm to do the optimization of some concrete examples for you instead. We will use some examples to show you the optimization step by step for you instead. Okay, so that's it for this class, and we'll continue to finish this section in the next class.